All right, so you finished your doodle notes. Now we're going to dive a little bit more into this. So how can we describe chemical reactions? All right, so keep your science notebook handy because there's going to be some stuff from here that I'm going to want you to write down in your notebooks to kind of hang on to for reference. Okay, so how would you describe making pancakes? Would you use the words a double replacement reaction or endothermic in your description? A chemist would describe making pancakes with chemical reactions and describe the changes in matter and energy involved in the reactions. As you'll learn, chemical reactions can be described by chemical equations and by how substances and energy change during a reaction. So, chemical reactions change the composition of a substance. Scientists describe chemical reactions using chemical equations. Here we go. First vocab that I want you to write down right here. A chemical equation is a shorthand way to communicate how substances change in a chemical reaction. Similar to the math equations you are familiar with, in chemistry, a chemical equation is called an equation because it shows that there are two sides to every reaction. Chemical equations are balanced between these two sides, just as math equations are. What ingredients go into making pancakes? What do you get as a result of mixing and cooking these ingredients? Just like the process by making pancakes, chemical reactions can also be described by the starting ingredients and the end results. Recall that the reactants are the substances that go into and are used up in the reaction. The products are the substances that are formed as a result of the reaction. So Tuesday's lesson, you should have written down what reactants and products were, but if you didn't, pause and get those down now, okay? Scientists write chemical equations, based on the reactants and the products in a reaction. Since the reactants are the starting substances, scientists write the reactants on the left side of the chemical equation. This way, you read the reactants before you read the products. It only makes sense, right guys? It only makes sense. I'm going to read what I start with before I read the finish. Are you one of those people who peeks and reads the end of the book before you decide if you're going to read the whole book? Oh, I know people who do that, and that just like irks me. Like, you can't read how the book ends before you start it. Why would I read how my equation ends before? Okay, so we start with the reactants, is my long way of saying that. Scientists write the products on the right side of a chemical equation to show that the products form as a result of the reaction. In the example below, we have one methane molecule here, CH4, reacting with two oxygen molecules, so 2O2, so 4 oxygens total. Okay, those are our reactants. Plus, then my arrow shows that carbon dioxide and water are the products. Okay, so I've got 2 of my oxygen here decided to grab hold of my carbon dioxide, and then I've got water. My other my hydrogens that were chilling with my methane here, they grabbed onto my other water molecules. So those are my resulting products. Do you know why there's a large number 2 in front of the oxygen, right here, and the water molecules in the equation? The number 2 is a coefficient. In chemical equations, the coefficient tells you how many molecules of each substance are in the reaction. You can use the coefficient to find the number of atoms of each element by multiplying the coefficient by the subscript, that means the tiny number, of each atom. Recall that if there's no subscript, this means there's only one atom of that element in the molecule, okay? So I've got a large number 2 to show that there are 2 oxygen molecules. And in each oxygen molecule, there's 2 of them. Bloop, 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 bloop. Okay, and then I can go 2 times 2 is 4. 4 total oxygens. Just like my coefficient here, the 2 shows that I've got 2 water molecules, right? As you can see, chemical equations are written with chemical symbols for each element, and then a chemical formula for each compound in the reaction. The arrow, here's my arrows, the arrows between the reactant and the product means yields. And the plus sign means reacts with, while on the right side it means and. So a fancy way of saying it is this reacts with this, which gives you this and this. The physical state of a substance is often written next to the substance in parentheses, solid, liquids, gases. Okay, so I could say 2Na, solid, chlorine 2, gas, gives me 2, what did this form? Sodium chloride, a solid, table salt. Okay, and then how would you use gumdrops and toothpicks to model the chemical reaction of sodium with chlorine? Too bad you ate all your gumdrops already, huh? So, Tuesday we looked at conservation of mass, then we did a lab on the conservation of mass. Let's review it just a little bit more. In the reaction of methane and oxygen gas, how do the numbers of each kind of atom compare in the reactants and products? You learned earlier that in chemical reactions, the law of conservation of mass states that no matter is created or destroyed in the reaction. Scientists show conservation of mass by writing balanced chemical equations for reactions. A balanced chemical equation shows that the number of atoms for each element is equal on both sides of the equation. So let's look at this a little bit. All right, let's talk about how much I struggled in chemistry class with this concept right here and how it very much so made my head hurt. That's okay, we can do this together. How would you write the chemical equation for the reaction between aluminum metal and oxygen gas to produce aluminum oxide? The chemical symbol for aluminum is Al, the chemical symbol for oxygen is O, and the compound aluminum oxide is written as Al2O3. So you might be tempted to write the following equation like that. Why does it always highlight the whole thing? But is this equation balanced? Count the number of atoms for each element on both sides. Is there an equal number of atoms for each element on both sides? Well, let's see, I've got 2 aluminums here, but I don't have 2 aluminums over there. Whoop. I've got 3 oxygens here, and I've got 2 oxygens there. That doesn't work. It's not balanced. So this is where math and science combine and form something beautiful. How would we actually show this? This is the correct balanced equation. 4 aluminums plus 3 oxygen molecules with 2 oxygens in them each puts a 2 in front, so a 2 coefficient of 2 aluminums and 3 oxygens. Because remember, the big coefficient 2 gets multiplied times the subscript. 2 times 2 equals 4. 2 times 3, 3 times 2, 6, 6, and it balances. And let me tell you guys, the first time that my science teacher in high school went over this stuff, I literally just stared at the board and I was like, I don't know where you just got those numbers from. This does not make sense. Don't worry. This is something that you're going to do a lot more of in high school chemistry with Mr. Claus, and he is a pro. Basically, the big takeaway is I've got to have the same stuff on one side as I do on the other side. I've got to have a balance. That's our conservation of mass. Matter can't just be taken away and done away with, all right? Stuff has to balance. Okay, so remember that coefficients show the number of molecules of each substance in a reaction. Scientists use coefficients to make the number of atoms of each element on both sides of the equation balance. How many atoms of oxygen are on each side of the balanced chemical equation for aluminum oxide? 6. 2 times 3 last time I checked. Using what you learned about coefficients in chemical equations, look at the 3 chemical equations below. Which ones are balanced? Okay, so here's how we would do this. If I see 2 carbons on this side, I'd better see 2 carbons on that side. Are there 2 carbons on that side? So A automatically is not balanced there. What about over here? I've got a coefficient, so that means some multiplication is going down. So 2 times 2, I need to see 4 carbons. I've got a big number in front of my carbon. 4 carbons? Okay, we're all right so far. 2 times 6, 12 hydrogens. 12 hydrogens. So I look over on this side of the arrow. 6 times 2, 12 hydrogens. Ooh, we're good so far. 7 times 2 oxygens. 14 oxygens. So now let's come over here and check this side of the arrow. 4 times 2, 8. 6 applies to all of it. 8 plus 6. Hey! Are we? Are we? What do you think? We're balanced. Okay. C. 1 potassium. 1 potassium. 3 chlorines. 3 chlorines. So here was one of the things that I think confused me a lot when I first got to seeing this, is how come there's a little itty bitty 3 here, but a big 3 there? Like, But it's because it's referring to how they're bonded together, like in their gumdrops and their toothpicks, okay? But it means the same thing, okay? So far we're balanced. 3 times 6, 6 hydrogens. Well, here I've got 3 hydrogens. Here I've got another 3 hydrogens. We're still balanced, and then this 3 applies to that oxygen too. So 3 oxygens, woo! Balanced, ka-ching. All right? So, oh man, hey look, they made a chart. I wish I'd seen that ahead of time. This is why technology, it might help you to make a chart to count the number of atoms of each element on each side of the equation. Below is an example for equation A. C2, but in the product I've only got 1 carbon. In the reactants I've got 4 hydrogens, but in the product I've only got 2. This is basically what we just did. And we can see that they aren't balanced. The reactants on that side of the equal sign does not balance with the products on this side. Okay, energy and chemical reactions. How would you describe a moving object? Would you use energy to describe a boulder sitting on top of a large hill? Just as scientists use energy to describe moving objects, scientists also describe chemical reactions in terms of energy. In a chemical reaction, the bonds between the atoms and molecules are broken or made, and new molecules are formed. Making and breaking bonds requires energy. This means that in all chemical reactions, some amount of energy changes from reactants to products, and this energy is usually in the form of heat. What chemical reactions help release heat and help you cook food? So, exothermic and endothermic. We should be used to these words, but we're going to write these terms down just so to help your memories. Similar to how total mass is conserved in chemical reactions, the total energy between a reaction and the surrounding environment is also conserved. Chemical reactions can either release heat into the environment or absorb heat from the environment. Whether a particular reaction releases or absorbs heat depends on the energy difference between the reactants and the products. If the reactants have more energy than the resulting products, it is an exothermic reaction and they release energy. So exothermic, release energy, gives off heat. Exothermic reactions feel hot to the touch because heat is released into the environment. If the reactants have less energy than the resulting products, it is an endothermic reaction. These reactions absorb energy in the form of heat, and endothermic reactions feel cold to the touch because heat is absorbed from the surrounding environment to use in the chemical reaction. Okay, so make sure you write those down in your notes. Okay, that's a lab we're going to do. The transfer of heat from a reaction to the environment can be measured as temperature change in the environment. Would you expect the temperature of the surrounding environment to increase or decrease with an endothermic reaction? Look at the diagrams below that show the energy change during exothermic and endothermic reaction, and given what you know, which diagram would best show the combustion of candle wax? Whew. So, What do you think when candle wax is melting? Like when you're burning a candle, are you absorbing energy or releasing energy? What do you think? Okay, so this goes along with our doodle notes, guys. Here we go. Types of chemical reactions. How would you describe the weather today? Well, I would say that it's a little bit sunny outside, but you still want a light sweater. Would you describe how sunny it is or what the temperature is outside? As you know, there's many ways to describe the weather. Similarly, there are many ways to describe how substances change in chemical reactions. In general, though, scientists describe the way substances change in two ways. One way is to describe how the atoms change their bonds with each other. A second way is to describe how electrons are exchanged between atoms. The names combustion, synthesis, decomposition, single or double replacement reactions all describe how atoms of reactants change bonds. The name oxidation-reduction reaction, such big words, describes how electrons are exchanged between atoms of reactants. As you learn about types of reactions, keep in mind that many reactions can be described both by how atoms change bonds with one another and by how the electrons are exchanged. Combustion reactions. When you observe something burning, you are actually observing a combustion reaction. Some of the reactions that break down sugar in living cells are also combustion reactions. Think about a combustion reaction that occurs in plants. Combustion reactions have three requirements: fuel source, oxygen, heat. Fuel sources can be hydrocarbons or molecules that are made up of many carbon and hydrogen atoms such as methane or propane. Fuel sources can also be substances such as glucose, which, as you know, is a simple sugar found in many types of cells. The reactants of the reaction are the fuel source and oxygen. The products are carbon dioxide and water. So here we see combustion of propane. We're left with carbon dioxide and water. Combustion of glucose in our bodies, resulting in carbon dioxide and water. Synthesis and decomposition reactions. In synthesis reactions, two elements or compounds react to form a single product. The formation of sodium chloride and the formation of water are examples of synthesis reactions. So these we're used to seeing, right? Sodium, chlorine, and we get table salt. Hydrogen, oxygen, and we get water. A decomposition reaction is the opposite of a synthesis. It occurs when compounds breaks into two or more simpler substances, like when we did our reversal and we were like evaporating to get our sea salt. There is usually only one reactant in decomposition reactions. For example, when you heat up magnesium chloride, it breaks down into magnesium and chlorine. So there's our example of a decomposition. Then single and double replacement. And in our notes, we called them displacement. Displacement and replacement, they mean the same thing. In single replacement reactions, a single element replaces another element, our switcheroo. There are usually two substances as reactants, an element and an ionic compound. For example, chlorine can replace sodium in sodium bromide to form sodium chloride plus bromine. In order for a single replacement reaction to occur, the single element must be more reactive than the element that is in the compound. Chemists have charts that list elements by their reactivity, and these charts help them determine whether a single element can replace another element in a compound. For example, copper is more reactive than silver, and because it's more reactive than silver, a copper atom can replace the silver atom in the compound silver nitrate. So here's our copper, and there's our silver nitrate, and all of a sudden our copper and our silver did the switcheroo. Okay, and what makes them more reactive? The amount of electrons in their outer orbital. How many valence electrons? You are correct. In double replacement reactions, two compounds exchange elements, double switcheroo. Most of these reactions occur in aqueous solutions, which means that compounds are dissolved in water. And chemists use the symbol AQ to show that compounds in the reaction are aqueous. Since these reactions are in water-based solution, if a product is insoluble, that means it can't dissolve, it's often a precipitate. The following example shows that the precipitate, silver chloride, forms in a double replacement reaction. So that's what we're seeing in this picture here. When copper wire is placed in aqueous silver nitrate, the product is silver and copper nitrate. So you can see we've got the double switcheroo. And let's just read our recap summary here. Chemical reactions can be described by matter and energy changes. Some descriptions are true for all chemical reactions. Matter is conserved within all chemical reactions, and energy is conserved within the overall reaction and its surrounding environment. Chemical reactions can be described by the energy or heat change that occurs. All chemical reactions transfer energy between the reaction and its surrounding environment. Exothermic reactions release heat into the environment, while endothermic reactions absorb heat from the environment. You can identify heat changes in a reaction by measuring the change in temperature surrounding a reaction. Chemical reactions can also be described by how matter changes, or the type of reaction that occurs. Common types of chemical reactions include combustion, synthesis, decomposition, single replacement, double replacement. All right, so you don't need to do these questions. Our doodle notes was what needed to happen for this one, okay? So we're going to be doing some more labs to illustrate these different types of chemical reactions, and then we're going to be doing more with chemical formulas, and we're just going to be diving into this stuff. So hopefully this all is starting to line up for you. All right, see ya.